33 trillion kilograms. That's the minimum mass astronomers are now attributing to our latest interstellar visitor, 3I Atlas. To put that in perspective, it outweighs the Empire State Building by a factor of 40,000. Yet, this cosmic heavyweight glides through space, producing active gas jets while showing virtually no orbital nudge from its own exhaust. It's like watching a freight train powered by birthday candles. But that's not even the weirdest part. Given its size, we should have found dozens of smaller objects before discovering such a giant. We didn't. Either our understanding of cosmic debris is fundamentally wrong, or we're witnessing something that challenges the very nature of what drifts between the stars. The numbers come from Harvard's Center for Astrophysics, where researchers passed 4,022 positional measurements from 227 observatories worldwide. This isn't speculation anymore. It's a lower limit, and while it's preliminary, the implications are staggering. Let's step back from the math for a moment. Astronomers saw virtually no measurable rocket push from outgassing. When a comet gets warm, ice turns to gas. That gas escapes, creating jets that nudge the comet like tiny thrusters. We've seen this countless times. But 3I Atlas shows active outgassing, water vapor, carbon dioxide, even exotic compounds. Yet the expected nudge isn't there. The only explanation that fits is mass. Lots of it. Why does this matter? Oumuamua showed anomalous acceleration that puzzled scientists for years. 2I Borisov behaved like a textbook small comet, reassuring in its familiarity. 3I Atlas introduces something new, a heavyweight that acts like an active comet, but shrugs off its own breath like a mountain ignoring morning mist. We're looking at a regime we've never seen before. The community reaction has been fascinating to watch. Astronomers express curiosity, mixed with healthy skepticism. The coverage summarizes the mass limit narrative accurately. But everyone stresses this hasn't undergone peer review yet. Its extraordinary claims meeting ordinary scientific process, exactly how it should work. But the tension is palpable. You can feel the field holding its breath. If 3I Atlas really has a 5-kilometer nucleus and weighs 33 billion tons or more, it's 3 to 5 orders of magnitude more massive than previous interstellar visitors. That's not a modest upgrade. That's jumping from pebbles to boulders in the cosmic debris field. It's like discovering mice by finding elephants first. Tonight, we examine the discovery that may be rewriting the rules of interstellar archaeology as we face an uncomfortable question. What else haven't we discovered yet? The telescope array sat high in the Chilean Andes, scanning the southern sky as it did every clear night. Atlas South, one of 4 robotic observatories designed to catch asteroids before they surprise us, captured something unusual on July 1st, 2025. Just another dot of light at first, moving against the backdrop of distant stars. The automated systems flagged it as potentially interesting. A human would need to look closer. Within hours, astronomers began the careful work of determining what they'd found. Early images suggested an asteroid, maybe a comet. The object received a temporary designation, a string of numbers and letters that meant nothing to anyone outside the minor planet center. But as more telescopes pointed toward this mysterious visitor, something strange emerged from the data. The orbit was wrong. Not wrong in the sense of miscalculation, but wrong in the sense that it didn't belong. The trajectory showed a hyperbolic path, the mathematical signature of an object passing through rather than orbiting around. This wasn't a local resident of our solar system. it came from somewhere else entirely. Recovery images helped confirm what astronomers suspected. These are archival photos taken before the official discovery, sometimes weeks or months earlier, that capture the object by accident. Researchers scoured databases of sky surveys, finding 3I Atlas in older images they hadn't noticed at the time. Each recovery image refined the orbital solution, strengthening the case that this visitor arrived from interstellar space. By mid-July, the evidence became undeniable. The Minor Planet Center, the organization responsible for cataloging solar system objects, reclassified the discovery. It received a new designation, C/2025N1, with the word Atlas in brackets. But everyone started calling it 3I Atlas. The 3I prefix meant third interstellar, a reminder of how rare these visitors truly are. The astronomical community buzzed with excitement. Since Oumuamua in 2017 and 2I Borisov in 2019, researchers had been hoping for another chance to study an interstellar traveler. Now they had one, and this time they were ready. Hubble Space Telescope time was requested immediately. The James Webb Space Telescope, still relatively new to operations, could provide unprecedented infrared observations. Ground-based observatories around the world began coordinating their efforts, creating a global network focused on this single object. The Vera Rubin Observatory, still in its commissioning phase, contributed early observations that would preview its future role in discovering these visitors. When fully operational, Rubin would scan the entire southern sky every few nights, potentially finding dozens of interstellar objects each year. 3I Atlas represented a prototype for this coming revolution. But even as telescopes swung toward the new visitor, early observations revealed puzzling characteristics. The object showed signs of activity, a faint glow suggesting gas and dust escaping from its surface. This meant it was behaving like a comet, warming as it approached the sun and releasing frozen volatiles into space. What astronomers didn't know yet was that this comet would refuse to follow the rules. The physics governing how comets move and respond to their own outgassing would seem to break down when applied to 3I Atlas. The measurements would point toward something massive, something that shouldn't exist based on everything we thought we knew about interstellar debris. The discovery timeline compressed what used to take months into mere weeks. Modern computing power, automated detection algorithms, and instant global communication transformed astronomical discovery from a slow, methodical process into something remarkably fast. From first detection to detailed characterization, 3I Atlas went from unknown to intensely studied in less than a month. July 1st, 2025 would mark the beginning of a mystery that would challenge fundamental assumptions about what drifts between the stars. Picture a garden sprinkler spinning on a summer lawn. Water shoots from its arms in all directions, and those jets of escaping water create forces that make the whole thing rotate. The sprinkler moves because of its own exhaust. This simple physics governs how comets behave in space, and it's called the rocket effect. When a comet approaches the sun, solar heat warms its icy surface. Frozen water, carbon dioxide, and other compounds turn directly from solid to gas without becoming liquid first. This process, called sublimation, creates jets of gas that blast away from the nucleus at hundreds of meters per second. Those escaping gases carry momentum, and physics demands that momentum be conserved. The comet must recoil slightly, like a gun kicking back when fired. Astronomers have detected these non-gravitational accelerations in hundreds of comets. It's routine physics, predictable and well understood. The jets create tiny but measurable pushes that alter orbital trajectories over time. Given enough precise measurements of a comet's position, you can detect these deviations from a purely gravitational path. 3I Atlas breaks this pattern completely. Between May 15th and September 23rd, 2025, 227 observatories worldwide contributed 4,022 positional measurements of the object. This represents one of the most comprehensive tracking campaigns ever mounted for any solar system body. Each telescope recorded where 3I Atlas appeared against the background stars, accurate to tiny fractions of an arcsecond. Think of it as cosmic detective work. Each positional measurement represents a single snapshot, like a frame in a long exposure photograph of orbital motion. String enough frames together and patterns emerge. Deviations from pure gravitational trajectories become visible as systematic residuals, the difference between where the object actually appears and where gravity alone would place it. The precision required to detect 3I Atlas's acceleration limit staggers the imagination. We're talking about positional shifts smaller than 1/28,000th of an arcsecond. To put that in perspective, it's like detecting the width of a human hair viewed from 20 kilometers away. Yet ground-based telescopes routinely achieve this precision through careful calibration and statistical analysis of multiple measurements. After months of observation, even tiny non-gravitational forces should produce measurable orbital deviations. The accelerations accumulate over time as position shifts that grow proportionally to 1/2 times acceleration times time squared. The upper limit sits at 15 meters per day squared. Convert that to more familiar units, and you get roughly 2 billionths of a meter per second squared. That's extraordinarily small, about 1/10,000,000th, the acceleration you'd feel in a gently moving elevator. But here's the puzzle. 3I Atlas shows clear evidence of outgassing. Water vapor streams away at hundreds of meters per second. Carbon dioxide creates an extended atmosphere, reaching hundreds of thousands of kilometers from the nucleus. Telescopes captured visible jets and a growing dust cloud. All the signatures of active sublimation are present. Despite this obvious activity, the expected orbital nudge simply isn't there. The acceleration limit sits below detection, essentially indistinguishable from pure gravitational motion. It's like watching someone swim through water without getting wet. Logically impossible, unless fundamental assumptions are wrong. Gas escaping at hundreds of meters per second carries momentum. Conservation laws are not suggestions. That momentum must transfer to the parent body. A typical 1-kilometer nucleus experiencing modest gas loss rates would show acceleration easily detectable by precision measurements. Yet 4,000 measurements from 200 observatories show nothing. The math becomes inescapable. If you see active gas production, but no measurable recoil, something has to give. Either the gas isn't escaping efficiently, which seems unlikely given the visible activity, or the object is massive enough to absorb the recoil without flinching. Current evidence points strongly toward the second option. 3I Atlas appears to be the freight train of interstellar objects, so massive that its own breath cannot move it. Before 2017, we had never confirmed an interstellar visitor passing through our solar system. Then came Oumuamua, and everything changed. Hawaiian astronomers spotted it on October 19th, 2017, using the Pan-STARRS telescope. The name means scout or messenger in Hawaiian, fitting for humanity's first confirmed visitor from beyond. But Oumuamua refused to behave like anything we'd seen before. It showed no visible signs of cometary activity, no tail, no coma of gas and dust, nothing to suggest it was releasing volatiles as it warmed near the sun. Yet precise measurements revealed something puzzling. The object was accelerating away from the sun faster than gravity alone could explain. Something was pushing it, but what? Scientists proposed various explanations. Maybe hydrogen ice was sublimating invisibly, creating thrust without visible emissions. Perhaps solar radiation pressure was acting on an unusually elongated, flat shape like a cosmic sail. Some researchers suggested it might be a fragment of a larger body, with unique properties we'd never encountered. The debate continues today, with no clear consensus on what Oumuamua actually was. Its measurements suggested something small, probably less than 1 kilometer in its longest dimension, weighing perhaps millions of tons. It tumbled as it traveled, rotating in complex ways that made determining its exact shape difficult. Then it vanished back into interstellar space, leaving more questions than answers. 2 years later, we got our second visitor, and this one was reassuringly normal. Crimean amateur astronomer Gennady Borisov discovered it on August 30th, 2019, using a telescope he'd built himself. 2I Borisov, as it became known, behaved exactly like solar system comets of similar size. It showed clear cometary activity with a visible tail. Spectroscopy revealed familiar water and carbon monoxide emissions. Its nucleus measured roughly 1 kilometer across. Most importantly, the non-gravitational acceleration matched expectations perfectly. The rocket effect worked exactly as physics predicted. Gas escaped, the comet recoiled, and the orbital changes aligned with theoretical calculations. 2I Borisov was comfortable, predictable proof that interstellar comets could behave just like homegrown ones. Astronomers breathed a collective sigh of relief. Whatever Oumuamua was, it seemed to be the exception rather than the rule. Interstellar space apparently contained normal comets that followed normal physics. The universe made sense again. Then came 3I Atlas. This third visitor occupies a completely different region of parameter space. It shows the activity expected from a comet, releasing gas and dust as it warms. But it rejects the physics that should govern that activity. The measurements point toward extraordinary mass, something that shouldn't exist based on everything we thought we knew about interstellar debris. Compare the three. The visitors and a pattern emerges, or rather, the absence of a pattern. Oumuamua showed acceleration without visible activity, the opposite of normal comet behavior. 2I Borisov showed both activity and acceleration in perfect alignment with expectations. 3I Atlas shows activity without acceleration, another violation of standard physics. We have 3 confirmed interstellar visitors, and each one behaves differently. One accelerates mysteriously, one behaves normally, and one is apparently too massive to be pushed by its own exhaust. With a sample size of 3, we can't even begin to understand what's typical versus exceptional in the population of objects drifting between stars. 3I Atlas forces us to confront the uncomfortable reality that we've barely begun to explore this new frontier. Each visitor reveals something unexpected, expanding our understanding while simultaneously demonstrating how little we actually know. Gemini's South Telescope in Chile captured 3I Atlas on August 27th, 2025, revealing an object in transition. The morphology was changing before astronomers' eyes as the interstellar visitor warmed on its approach toward the Sun. The early Hubble images from July had shown predominantly the unusual sunward glow, that forward-pointing feature that seemed to defy expectations about how comet debris should behave. By late August, the picture had grown more complex. A more traditional anti-solar tail began emerging, material streaming away from the Sun in the classic pattern everyone expects from active comets. The object was developing dual personality. On one side, the persistent forward glow that had puzzled observers since discovery. On the other, a growing tail pointing in the opposite direction, away from solar radiation and wind. The comet was essentially showing tails in both directions simultaneously, a morphological circus that complicated efforts to understand its true nature. This evolution wasn't random. As 3I Atlas moved closer to the Sun, different regions of its surface experienced different heating conditions. Temperature gradients across the nucleus meant some areas sublimated more actively than others. The changing solar angle altered which jets were illuminated and how dust scattered sunlight back toward Earth-based telescopes. The dust-to-gas ratio became increasingly important for interpreting these observations. Comets don't just release gas when they warm. Tiny solid particles get swept along with escaping vapors, creating visible clouds and tails. The relative amounts of dust versus gas affect everything from how bright the comet appears to how efficiently momentum transfers between sublimating ice and the solid nucleus. If 3I Atlas produces more dust relative to gas than typical comets, or if its dust grains have different size distributions or compositions, that could alter the relationship between visible activity and expected acceleration. Understanding this balance requires combining observations across multiple wavelengths and techniques. Visible light images reveal dust scattering and overall structure. Infrared spectroscopy maps gas emissions and measures temperatures. Radio observations can sometimes detect molecular transitions that trace production rates directly. Each wavelength tells part of the story, and only by combining them do astronomers build complete pictures of what's actually happening. The morphological changes documented by Gemini and other facilities provided time series data crucial for testing models. As 3I Atlas warmed, different volatile species began sublimating at different rates. Water ice becomes active around 3 astronomical units from the Sun. Carbon dioxide starts much earlier, at greater distances. Exotic species each have their own characteristic temperatures, where they transition from solid to gas. This chemical evolution should correlate with morphological changes. Different gas species drive different dust entrainment processes. Carbon dioxide jets might create different dust patterns than water vapor jets. The fact that 3I Atlas's appearance continued evolving through the observation period confirmed active sublimation responding to changing conditions. But the evolving morphology also created challenges for the mass calculations. Positional measurements track the brightness-weighted center of the comet, not necessarily the physical nucleus itself. If the dust distribution shifts systematically as activity patterns change, the apparent position could shift even without real acceleration. Careful analysis must separate genuine orbital dynamics from photometric artifacts. The unusual morphology, combined with the missing acceleration signal, meant astronomers had to work harder than usual to ensure their conclusions about mass rested on solid foundations, rather than observational illusions created by complex light scattering. The story of 3I Atlas unfolds through the collective vision of hundreds of telescopes scattered across Earth's continents. When researchers compiled their analysis, they drew from 4,022 individual measurements contributed by 227 observatories between May 15th and September 23rd, 2025. This represents one of the most comprehensive tracking campaigns ever mounted for any celestial visitor. Astrometry, the precise measurement of positions in the sky, forms the backbone of how we understand orbital motion. Every telescope that points at 3I Atlas records where it appears against the background stars, noting its position in celestial coordinates that work like longitude and latitude for the sky. These measurements, accurate to tiny fractions of an arcsecond, accumulate into a detailed map of the object's path through space. Think of it as cosmic detective work. Each positional measurement represents a single snapshot, like one frame in a long photographic exposure of orbital motion. String enough frames together and patterns emerge. Deviations from pure gravitational trajectories become visible as systematic differences between where the object actually appears and where gravity alone would place it. The precision required to detect 3I Atlas's acceleration limit staggers the imagination. We're talking about positional shifts smaller than 1/28,000th of an arcsecond. To put that in perspective, it's like detecting the width of a human hair viewed from 20 kilometers away. Yet ground-based telescopes routinely achieve this precision through careful calibration and statistical analysis of multiple measurements. How does this translate to physical acceleration limits? The relationship involves orbital mechanics and geometry, but the basic physics is straightforward. Small accelerations accumulate over time as position shifts that grow proportionally. After months of observation, even tiny forces should produce measurable orbital deviations. The upper limit of 15 meters per day squared emerges from this analysis. Convert to more familiar units, and you get roughly 2 billionths of a meter per second squared. That's extraordinarily small, about 1/10 millionth the acceleration you'd feel in a gently moving elevator. This level of precision transforms asteroids and comets from fuzzy dots into precisely mapped trajectories, where even subtle deviations from pure gravity become detectable. Each observatory contributes its unique expertise and geographical perspective. Northern Hemisphere sites track 3I Atlas during their summer months, while southern observatories take over as Earth's rotation brings different sky regions into view. The discovery timeline compressed what once took months into weeks. Atlas Chile first spotted the object on July 1st. Within weeks, the Minor Planet Center reclassified it as humanity's third confirmed interstellar visitor. Amateur astronomers and professional collaborations fed early observations into the global database. These measurements, while perhaps less precise individually than major observatory data, provide crucial temporal coverage. They help characterize how the object's brightness and appearance evolved as it warmed approaching the sun. The global coordination required for this campaign showcases modern astronomy at its collaborative best. Observatories across time zones maintain continuous coverage as Earth's rotation carries each site into darkness. Data flows to central databases where analysts compile measurements into increasingly refined trajectory solutions. What makes this particularly impressive is the speed. Unlike historical discoveries that might take months or years to confirm, 3I Atlas went from initial detection to detailed characterization within weeks. Modern computing power, automated algorithms, and rapid communication networks compress timelines that once stretched across seasons. The measurement precision explains how researchers could place such tight constraints on acceleration. When you have thousands of positions measured to extraordinary accuracy over months, systematic deviations from gravitational motion become statistically significant, even if they're physically tiny. The Global Telescope Network essentially transformed Earth into a single planet-sized instrument with baseline separations spanning continents. The Very Large Telescope in Chile turned its powerful spectrographs toward 3I Atlas during August 2025 observations. What the instruments revealed added yet another layer of strangeness to an already puzzling object. Multiple nickel emission lines blazed prominently in the infrared spectrum, while iron remained conspicuously absent. This chemical asymmetry challenges basic assumptions about how metals appear in cometary environments. In most astronomical contexts, nickel and iron show up together because they form from similar processes and often exist in similar chemical compounds. Seeing one without the other is genuinely unusual. The observation itself is straightforward but striking. VLT's high-resolution instruments detected several nickel atomic transitions in the 700 to 900 nanometer wavelength range. These lines appeared clearly above background noise levels, strong enough to allow detailed analysis of nickel production rates and how the metal was distributed within the surrounding gas cloud. Iron lines should have appeared at nearby wavelengths. Astronomers expected to find them based on decades of comet observations, but the spectra showed only noise where iron emissions should be. This wasn't simply a failure to detect weak signals. The absence represents a genuine chemical peculiarity that demands explanation. Context makes the anomaly more significant. Nickel and iron commonly exist together in meteoritic materials and comet dust. Finding abundant nickel without corresponding iron is like discovering a forest full of oak trees, but no maples in a region where both species normally coexist. Something about 3I Atlas's composition, or the processes releasing metals into its atmosphere, operates differently than in typical comets. The production rates showed steep scaling as 3I Atlas approached the Sun. Both nickel and another compound called cyanogen increased dramatically with decreasing solar distance, following mathematical relationships that indicated strong temperature dependence. This rapid brightening suggests whatever process releases these materials operates near a critical temperature threshold. As solar heating warms the surface, some mechanism suddenly becomes efficient at liberating nickel atoms into the surrounding gas, where they emit the observed spectral lines. The mathematics of this temperature dependence provides clues about underlying chemistry and physics, though the exact processes remain uncertain. Traditional explanations for metallic emissions in comets involve several possible mechanisms. Direct sublimation of metal-rich minerals typically requires much higher temperatures than 3I Atlas experienced at the distances where VLT observed it. Something more subtle must be operating. One possibility involves what scientists call photostimulated desorption. Solar ultraviolet radiation can break chemical bonds in surface materials, liberating atoms that would remain bound under purely thermal conditions. If 3I Atlas contains nickel-bearing compounds that are particularly susceptible to this process, while iron-bearing materials remain more tightly bound, this could explain the selective appearance of nickel. Another hypothesis involves breakdown of organic metallic compounds or metal carbonyl complexes that might exist in the nucleus. These materials can decompose at relatively low temperatures, releasing metal atoms through chemical breakdown rather than direct sublimation. If nickel forms more volatile compounds than iron in the interstellar environment where 3I Atlas originated, differential release could produce the observed pattern. What this chemistry does not prove deserves emphasis. Some media coverage noted that nickel without iron resembles certain industrial alloy compositions and suggested technological interpretations. This represents a logical leap unsupported by spectroscopic evidence. Metal emissions in comets come from well-understood atomic physics, not engineering processes. The VLT team presented their results as interesting examples of unusual but natural chemistry, not evidence for manufactured objects. Distinguishing between genuine scientific anomalies and sensationalized misinterpretation matters for public understanding. Unusual chemistry deserves investigation and explanation, but unusual doesn't automatically imply artificial. The James Webb Space Telescope pointed its infrared instruments toward 3I Atlas on August 6, 2025. What it found added another puzzle piece to an already mysterious picture. JWST's near-infrared spectrograph detected not just the usual suspects like water ice and water vapor, but also carbon dioxide and carbon monoxide in unusual proportions. The carbon dioxide to water ratio ranked among the highest ever measured in a comet at this distance from the Sun. This wasn't just slightly elevated, it was dramatically different from typical solar system comets. Most comets formed closer to their parent stars, where water ice dominates the chemical mix. Carbon dioxide exists in these comets too, but usually in smaller amounts relative to water. 3I Atlas flipped this expectation. Its atmosphere showed carbon dioxide in abundances that suggested something fundamentally different about where and how it formed. The chemical signature points to birth in the frigid outer reaches of some distant solar system. Astronomers call this region beyond the carbon dioxide snowline, where temperatures drop below -125 degrees Celsius. At these extreme cold temperatures, carbon dioxide freezes solid alongside water ice, getting incorporated into forming comets in much higher proportions. Think of it as a frozen memory. The ice inside 3I Atlas condensed from gas billions of years ago, in conditions so cold that carbon dioxide became a major component rather than a trace element. The object has been traveling through interstellar space ever since, preserving that primordial chemistry like a time capsule from an alien stellar system. The Spherex Space Telescope, designed for infrared surveys, detected an extended carbon dioxide atmosphere reaching hundreds of thousands of kilometers from the nucleus. That's enormous, far larger than the compact, bright region visible in optical wavelengths. The visible light shows a relatively small glowing area, but infrared reveals a massive invisible envelope surrounding the solid core. This chemical data matters for understanding 3I Atlas's mass because it affects how we interpret the outgassing. Different volatile compounds sublimate at different rates and temperatures. Carbon dioxide becomes active much farther from the Sun than water ice. If 3I Atlas is dominated by carbon dioxide-rich ice, its activity patterns might differ from water-dominated comets in ways that affect momentum transfer calculations. The gas production estimates that feed into mass calculations depend on understanding what's actually sublimating and at what rates. JWST's spectroscopy provides crucial constraints on these questions. The high carbon dioxide content suggests the object formed in extremely cold conditions. But it also means the chemistry driving its current activity might not match typical comet models based on water-ice sublimation. Water ice becomes active around 3 astronomical units from the Sun. Carbon dioxide starts sublimating much earlier, at greater distances where solar heating is weaker. This means 3I Atlas was likely active long before astronomers discovered it, potentially losing mass through outgassing during its long approach through the outer solar system. The enrichment in carbon dioxide and carbon monoxide paints a picture of an object born in darkness and cold, in the outermost regions of a planetary system where sunlight barely reaches. These are the conditions where giant planets form, where ice and rock accumulate into massive bodies over millions of years. Whatever stellar system ejected 3I Atlas into interstellar space, it came from the cold frontier of that alien solar neighborhood. But the chemistry also raises questions about how typical or exceptional this composition might be. Are all interstellar comets enriched in carbon dioxide, or does 3I Atlas represent a special case? With only 3 confirmed visitors and detailed chemistry for just 2 of them, we simply don't know yet what's normal in the population of objects drifting between stars. The math is straightforward, but the implications are staggering. When you combine visible cometary activity with virtually no measurable acceleration, only one variable can absorb the contradiction: mass. Extraordinary amounts of mass. Let's walk through the calculation step by step. Astronomers estimate 3I Atlas loses roughly 150 kilograms of material per second through outgassing. That sounds modest, about the weight of 2 people every second. But over days and weeks, the cumulative momentum transfer should nudge even a substantial object into a measurably non-gravitational orbit. The gas escapes at approximately 440 meters per second. We know this from spectroscopic analysis of emission line profiles. When gas leaves a comet nucleus, thermal motion and bulk flow combine to broaden spectral lines in characteristic ways. Modeling these line shapes provides velocity estimates, and 440 meters per second falls within the normal range for active comets. Now comes the physics that cannot be avoided. Momentum must be conserved. It's not a theory or a model. It's a fundamental law of nature. If 150 kilograms of gas shoots away from the nucleus every second at 440 meters per second, that gas carries momentum. The nucleus must recoil in the opposite direction. For a typical 1-kilometer comet nucleus, this recoil would be easily detectable. The acceleration would show up clearly in positional measurements after just a few weeks of observation. But 3I Atlas shows acceleration below 15 meters per day squared, which translates to roughly 2 billionths of a meter per second squared. That's essentially 0 for practical purposes. The only way to reconcile these facts is if the nucleus is far more massive than a typical comet. Using standard comet densities around 500 kilograms per cubic meter, the 33 billion ton lower limit corresponds to a nucleus at least 5 kilometers in diameter. That's genuinely enormous by interstellar visitor standards. To put this in perspective, imagine trying to move a freight train by throwing tennis balls at it. The balls bounce off, carrying momentum away, but the train doesn't budge. An observer would quickly realize they're dealing with something much more massive than appearances might suggest. 3I Atlas appears to be the freight train of interstellar objects. But these numbers come with important caveats that careful scientists always mention. The mass estimates depend heavily on assumptions about outflow rates and gas velocities. Change those assumptions, and the mass estimates change accordingly. The James Webb Space Telescope observed 3I Atlas on August 6, 2025, providing crucial spectroscopic data about what's actually sublimating. Those measurements inform the models that connect visible activity to invisible mass. The outflow rate of 150 kilograms per second isn't directly measured. It's derived from models of how much gas would be needed to create the observed brightness and extent of the coma. Different modeling assumptions could yield different production rates. The gas velocity of 440 meters per second comes from spectral line analysis. But that too involves assumptions about temperature distributions and gas dynamics. Still, the basic physics is hard to argue with. If you see substantial gas production captured by multiple space telescopes and confirmed by ground-based observations, but no measurable rocket effect despite months of precise positional tracking, something fundamental must explain the disconnect. Either the gas isn't escaping efficiently, which contradicts the visible evidence, or the object absorbs the recoil without flinching because of extraordinary mass. The current evidence favors mass as the explanation. 3I Atlas appears to be genuinely, anomalously massive, a quiet giant masquerading as an ordinary comet until precision measurements revealed its true nature. The Hubble Space Telescope turned its gaze toward 3I Atlas on July 21, 2025, just 3 weeks after discovery. What it captured stopped astronomers in their tracks. Instead of the classic comet appearance, a bright nucleus trailed by dust streaming away from the sun. 3I Atlas displayed what observers described as a teardrop-shaped cocoon. But the truly unusual feature was a pronounced glow pointing toward the sun, rather than away from it. This forward-directed feature, called an anti-tail, challenged basic intuitions about how comet debris should behave. Most comet tails point away from the sun, swept outward by solar wind and radiation pressure. It's one of astronomy's most reliable visual cues, so predictable that ancient Chinese astronomers used comet orientations as celestial compasses. When you see material apparently pointing toward our star, your brain immediately struggles to reconcile the image with physics. Anti-tails aren't completely unprecedented in solar system comets. They can result from viewing geometry, when Earth's orbital position creates an illusion of sunward pointing material. Sometimes, larger dust particles follow ballistic trajectories different from fine dust swept by radiation pressure, creating apparent forward features when viewed from specific angles. The mathematics work out, but the visual impact remains startling. What made 3I Atlas unusual was the persistence of this sunward glow. This wasn't a brief geometric illusion that disappeared when viewing conditions changed. The forward-directed feature remained prominent through July and August as multiple observatories tracked the object. The consistency suggested real physical processes, rather than simple perspective effects. Recent modeling papers explain the phenomenon through sublimating grain physics. As ice-rich particles escape the nucleus, they continue releasing gas while traveling outward. Under certain conditions, this process can create apparent sunward features when viewed from specific angles. The explanation makes sense, but requires unusual combinations of dust properties and viewing geometry. By August 27th, Gemini South Telescope observations revealed the situation growing more complex. A more traditional anti-solar tail began emerging alongside the sunward glow. The morphology was evolving in real time as the object warmed approaching the sun. Early images showed primarily forward scattering, while later observations developed the classic dual tail structure with material streaming both toward and away from the sun. This evolving appearance matters for a crucial reason. Dust to gas ratios and grain lifetimes affect how bright the comet appears, and, critically, where its brightness center falls relative to the actual nucleus. Since positional measurements track this brightness-weighted center rather than the physical nucleus itself, systematic changes in appearance could potentially bias the orbital solutions. The challenge lies in separating genuine dynamics from visual artifacts. If 3I Atlas's unusual morphology systematically shifts where its brightness appears brightest, that could mimic or mask real accelerations. Careful analysis must account for these effects to avoid drawing incorrect conclusions about mass and dynamics. The sunward glow might result from forward scattering by dust grains with specific size distributions and compositions. When particles scatter sunlight preferentially toward the observer rather than away from the sun, they can create brightness enhancements that appear to violate basic physics. The effect is real, the light truly is there, but the interpretation requires understanding of how different grain properties affect scattering patterns. Still, Hubble's images captured something genuinely unusual. While anti-tails have appeared in solar system comets before, the early prominence and persistence in 3I Atlas pushed into less familiar territory. Combined with the missing acceleration and extreme mass estimates, the morphology added another layer to an already puzzling object. It was as if 3I Atlas was determined to violate expectations at every possible level. The visible light images of 3I Atlas show a relatively compact glowing region, maybe a few thousand kilometers across at most. But that's only part of the story. Switch to infrared wavelengths, and an entirely different picture emerges. Spherex, the space-based infrared telescope, detected an extended carbon dioxide atmosphere reaching hundreds of thousands of kilometers from the nucleus. That's not a typo. Hundreds of thousands of kilometers. For comparison, Earth's moon orbits at about 384,000 kilometers. The invisible carbon dioxide envelope surrounding 3I Atlas approaches planetary scale dimensions. This creates a profound disconnect between appearance and reality. What looks like a modestly sized comet in optical images is actually wrapped in an enormous gaseous cocoon, visible only to infrared instruments. The solid nucleus sits at the center, like a tiny seed inside a massive fruit. The extended atmosphere matters for several reasons. First, it demonstrates that 3I Atlas is far more active than casual telescope images might suggest. Carbon dioxide, sublimating from the surface, doesn't just disappear. It expands outward, creating this vast, invisible shell that surrounds the object like a ghostly presence. Second, the size of this carbon dioxide cloud provides independent constraints on gas production rates. the bigger the cloud and the longer it persists, the more gas must be escaping from the nucleus to maintain it. Solar wind and radiation pressure work constantly to blow this material away. So, a sustained large envelope requires continuous replenishment from the central body. Third, the extended coma affects how we interpret brightness measurements. When astronomers measure the object's position, they're actually tracking the center of brightness, not necessarily the physical nucleus location. If the gas and dust distribution is asymmetric, which it clearly is given the unusual morphology, the brightness center might not coincide with where the solid body actually sits. This photometric effect could potentially introduce systematic errors into position measurements, if not properly accounted for. Imagine trying to track a streetlight in fog. The glow you see is centered somewhere near the actual bulb, but exactly where depends on how the fog scatters light. 3i Atlas presents a similar challenge, with its extended atmosphere creating a complex light scattering environment. The carbon dioxide dominance in this extended envelope reinforces the chemical story told by JWST spectroscopy. This isn't a water-dominated comet like most we're familiar with. Carbon dioxide drives much of the activity, creating an atmosphere with different properties than typical water-rich cometary comas. Carbon dioxide sublimates at lower temperatures than water ice, meaning it becomes active farther from the Sun. 3i Atlas was likely producing this extended carbon dioxide envelope long before astronomers discovered it, possibly for months or even years as it approached through the outer solar system. The invisible nature of this massive atmosphere to optical telescopes demonstrates why multi-wavelength observations are crucial for understanding these objects. Relying only on visible light would miss the majority of what's actually happening. Infrared, radio, ultraviolet, each wavelength reveals different components of the complete picture. The paradox deepens when you consider that all this gas escaping to create the enormous envelope should be pushing the nucleus in the opposite direction through momentum conservation. Yet, the acceleration measurements show virtually nothing. Either the extended coma we're observing doesn't represent as much mass loss as it appears, or the nucleus absorbing that recoil is extraordinarily massive. The 33 billion ton mass estimate for 3i Atlas isn't a direct measurement. It's the endpoint of a chain of inferences, each link depending on assumptions that could potentially be wrong. Understanding this chain matters for evaluating how confident we should be in the extraordinary claims about this object's size. Start with what we actually observe. Telescopes detect light from gas and dust surrounding the nucleus. Spectroscopy reveals which molecules are present and provides clues about their velocities and temperatures. These are the raw observations, the data we can trust because multiple independent facilities confirm them. From spectral line profiles, researchers estimate gas escape velocities around 440 meters per second. This number comes from analyzing how emission lines are broadened by the motion of gas atoms. Faster moving gas creates broader spectral features. The velocity estimate involves assumptions about temperature distributions and whether the gas flows uniformly or in jets, but 440 meters per second falls within normal ranges for active comets. Next comes the outflow rate estimate of 150 kilograms per second. This isn't directly measured. Instead, researchers model how much gas would be needed to create the observed brightness and extent of the atmosphere. The calculation requires assumptions about how efficiently different molecules emit light, how the gas density falls off with distance from the nucleus, and how much of the escaping material we're actually seeing versus missing. Different modelling approaches could yield different production rates. A factor of 2 uncertainty in the outflow rate translates directly into a factor of 2 uncertainty in the final mass estimate. If the actual gas production is only 75 kilograms per second instead of 150, the mass estimate drops proportionally. The momentum transfer efficiency adds another layer of uncertainty. When gas escapes, does all its momentum transfer to the nucleus, or do some complicated surface effects reduce the efficiency? Laboratory studies of sublimation suggest the process is usually quite efficient, but 3I Atlas might have unusual surface properties that change this relationship. The assumed density of 500 kilograms per cubic meter comes from studies of solar system comets. But we don't know if interstellar visitors have the same bulk properties. A denser nucleus would be smaller for the same mass. A fluffier structure would require a larger diameter to reach 33 billion tons. Each assumption in this chain seems reasonable individually. Gas velocities are constrained by spectroscopy. Outflow rates are estimated from standard models. Momentum transfer should follow basic physics. Density estimates come from decades of comet research, but assumptions compound. Small uncertainties at each step can multiply into larger uncertainties in the final result. This is why the researchers emphasize their number as a lower limit rather than a precise measurement. The logic works like this. If we assume fairly conservative values for all these parameters and still get a huge mass, the actual mass probably is genuinely large. Even if some assumptions are somewhat off, you'd need everything to be wrong in the same direction to bring the mass estimate down to ordinary comet values. The JWST team hasn't released their definitive measurements yet. When they do, those numbers will either strengthen or weaken the case for extraordinary mass. Independent analysis by other research groups will test whether different modelling approaches converge on similar answers, or produce wildly different results. Population statistics tell us we're discovering interstellar visitors in the wrong order. Finding 3I Atlas before encountering dozens of smaller objects is like discovering mice by stumbling across elephants first. Something doesn't add up. Think about how planetary systems eject debris into interstellar space. Gravitational interactions during planet formation can fling objects onto escape trajectories. Stellar flybys can destabilize outer system bodies. Disk instabilities in young systems can scatter material outward. Every plausible mechanism shares one characteristic. Smaller objects get ejected more easily than larger ones. The physics is straightforward. Less massive debris requires less energy to accelerate to escape velocity. A Jupiter-sized planet can easily kick a kilometer-scale comet into interstellar space through a gravitational encounter. But launching something the size of 3I Atlas, potentially 5 kilometers across, and weighing 33 billion tons, requires much more specific conditions and energy transfer. Beyond ejection physics, detection biases should also favor smaller objects, at least within certain size ranges. While the tiniest debris becomes invisible to current surveys, objects in the 100-meter to kilometer range should be detectable when they pass through the inner solar system and develop visible activity. We have telescopes sensitive enough to spot these visitors if they're out there. Yet, our first 3 interstellar discoveries span a dramatic mass range. Oumuamua probably weighed millions of tons. 2I Borisov contained billions of tons of material. 3I Atlas potentially outmasses both by factors of 10 to 1,000. This progression defies naive statistical expectations. We should be swimming in small interstellar visitors and only occasionally spotting large ones. Several explanations might resolve this puzzle. Wide-field surveys like ATLAS and Catalina Sky Survey only recently achieved the sensitivity and coverage needed to routinely detect interstellar objects. The Vera Rubin Observatory, which will revolutionize the field, is just entering operations. We might be severely undersampling the actual population, seeing only the tip of a much larger iceberg. The detection order could reflect geometric coincidence rather than intrinsic rarity. 3I Atlas approached along a trajectory nearly aligned with the ecliptic plane, making it easier to spot than objects with highly inclined orbits. Its favorable geometry might have compensated for what would otherwise be low detection probability for such rare, massive objects. Alternatively, small interstellar debris might not survive the journey between stars. Erosion by cosmic rays, collisions with interstellar dust, or sublimation during chance stellar encounters could preferentially destroy smaller objects. If debris with diameters less than a few hundred meters gets sandblasted away during million-year journeys through space, the surviving population reaching our solar system could be biased toward larger, more robust specimens. But even accounting for these effects, 3I Atlas remains statistically uncomfortable. Population models that successfully explain asteroid belt demographics and Kuiper belt structure struggle to accommodate such massive interstellar visitors appearing so early in our discovery sequence. Either the models need updating, or 3I Atlas represents a genuinely rare event that happened to occur during humanity's first serious surveys. The sample size of 3 remains the fundamental problem. We're trying to understand the demographics of an entire galactic population based on 3 examples. It's statistically meaningless for drawing broad conclusions. Extreme outliers can completely distort inference when sample sizes are this small. The journey between stars is not a gentle cruise through empty space. Interstellar travelers face a gauntlet of hazards that might preferentially destroy smaller objects, explaining why we're finding massive visitors like 3I Atlas before encountering their smaller cousins. Cosmic rays bombard everything moving through the galaxy. These high-energy particles, mostly protons, traveling at nearly the speed of light, slam into exposed surfaces and gradually erode them. Over million-year timescales, typical for interstellar journeys, this radiation damage accumulates. Smaller objects have higher surface area to volume ratios, meaning a larger fraction of their total mass sits exposed to cosmic ray bombardment. Think of it like sandpaper wearing down a wooden block. A small block disappears faster than a large one because more of its volume sits near the surface. Similarly, a 100-meter comet might lose a significant fraction of its mass to cosmic ray erosion during a 10 million year journey between stars, while a 5-kilometer object like 3I Atlas barely notices the damage. Collisions with interstellar dust present another hazard. Space between stars isn't perfectly empty. Microscopic grains drift through the void, and objects traveling at tens of kilometers per second relative to this dust experience impacts like constant micrometeorite bombardment. Each grain carries tremendous kinetic energy at these velocities, chipping away at surface materials grain by grain. Again, smaller objects suffer disproportionately. A 100-meter body might fragment entirely from accumulated collision damage over millions of years, while a massive object shrugs off the same impacts as superficial surface weathering. Thermal cycling provides a third destruction mechanism. When interstellar objects pass near other stars during their journeys, they experience heating and cooling cycles that create internal stresses. Ice sublimates from the surface, then refreezes in different patterns. Rock and ice expand and contract at different rates. These thermal stresses can crack smaller bodies into fragments. Larger objects fare better because their interiors remain insulated from temperature swings. The surface might experience wild temperature variations, but the deep interior stays cold and stable. Smaller bodies lack this thermal buffering, meaning temperature changes propagate through their entire volume. If these destruction mechanisms operate efficiently, the population of interstellar objects reaching our solar system could be strongly biased toward survivors large enough to withstand the journey. The galaxy might eject plenty of small debris, but most of it doesn't survive long enough to cross the light years between stars. This survivorship hypothesis offers an elegant resolution to the population paradox. We're not necessarily finding elephants before mice, because elephants are more common. We might be finding them first, because the mice don't survive. The journey. The original ejected population could follow expected statistical distributions, but selective destruction during transit reshapes what actually arrives. Testing this hypothesis requires understanding destruction rates for different size objects under realistic interstellar conditions. Laboratory experiments can simulate cosmic ray damage and micrometeorite impacts, but extrapolating to million-year timescales involves uncertainties. Computer models can estimate thermal stress evolution, but they depend on assumptions about internal structure and composition. The galaxy operates as a vast redistribution network for planetary debris. Understanding how objects like 3I Atlas get launched into interstellar space requires examining three primary mechanisms, each with different efficiencies for ejecting material of various sizes. Planet-to-planet gravitational scattering dominates current theoretical frameworks. During the chaotic early phases of planetary system formation, massive bodies migrate through interactions that can fling smaller objects onto escape trajectories. Think of it as cosmic billiards, where planets act as cue balls, striking asteroids and comets hard enough to launch them into the void between stars. The physics strongly favors smaller projectiles. Launch velocity scales inversely with object mass for a given gravitational encounter. A Jupiter-sized planet can easily eject kilometer-scale comets, accelerating them beyond escape velocity through close approaches that last only hours or days. But launching something the size of 3I Atlas requires much more specific geometric conditions and energy transfer. The encounter has to be nearly perfect, with the massive planet passing at just the right distance and angle to impart sufficient velocity without simply destroying the object through tidal forces. Stellar flybys provide an alternative mechanism, particularly important in young stellar clusters where stars form close together. When another star passes within a few hundred astronomical units of a planetary system, its gravitational influence can destabilize outer system objects and scatter them onto escape trajectories. The efficiency depends on flyby speed, closest approach distance, and the architecture of the target system's outer regions. These encounters can potentially eject larger objects than planet-to-planet scattering. Since stellar masses exceed planetary masses by factors of hundreds or thousands, a close pass by a solar mass star could conceivably launch objects weighing billions or tens of billions of tons. This makes stellar flybys a plausible mechanism for creating visitors like 3I Atlas, though such encounters remain relatively rare even in dense stellar environments. Disk instabilities during the earliest phases of system formation represent the third major pathway. Before planets fully form, gravitational instabilities in massive protoplanetary disks can create spiral density waves and other asymmetric structures that scatter embedded objects. This process operates during the first few million years of stellar evolution, when disks still retain significant mass in gas and dust. The challenge lies in timing. Protoplanetary disks typically dissipate within 5 to 10 million years due to photoevaporation by stellar radiation and accretion onto the central star. If disk instabilities represent an important ejection mechanism for massive objects, the process must operate efficiently during these brief early phases. Objects like 3I Atlas would need to form and get ejected before their parent disks disappear, imposing tight timing constraints. Different stellar environments likely produce different ejection signatures. Young clusters versus isolated field stars, metal-rich versus metal-poor systems, binary versus single-star configurations. Each creates unique conditions affecting which mechanism dominates and what size distribution results. Imagine trying to understand human height distribution after measuring only 3 randomly selected people. You might get someone who's 5'2", someone who's 5'10", and someone who's 6'8". From this sample, what could you conclude about typical human height? Almost nothing. The tall person might be an extreme outlier or perfectly average. You simply cannot tell with 3 data points. This is exactly the situation astronomers face with interstellar visitors. Oumuamua arrived in 2017, strange and elongated, accelerating without visible gas emissions. 2I Borisov followed in 2019, reassuringly normal and comet-like in every way. Now, 3I Atlas in 2025, potentially the most massive of all, despite expectations that we should find smaller objects first. 3 examples, 3 completely different profiles, 0 statistical power to draw meaningful conclusions. The mathematical reality is harsh. With a sample size of 3, even the most extreme outlier could represent the typical case. We have no way to distinguish between normal variation within a population versus genuinely exceptional specimens. Every statistical tool requires larger samples to function properly. Confidence intervals become meaningless. Distribution shapes remain unknowable. Population parameters cannot be estimated reliably. Consider what this means for the mass puzzle. If 3I Atlas really weighs 33 billion tons, it could represent one of 3 scenarios. First, maybe massive interstellar objects are common, and we'll find many similar visitors as surveys improve. Second, perhaps it's a genuine statistical fluke, the equivalent of measuring that 6'8" person first. Third, possibly our detection methods systematically favor massive objects despite theoretical expectations otherwise. With only 3 examples, we cannot distinguish between these possibilities. The data permits all 3 interpretations equally. Adding speculation on top of such a small sample is like building a skyscraper on quicksand. The foundation simply isn't there. Population statisticians have a rule of thumb. You need at least 30 samples before you can begin making reliable inferences about underlying distributions. Ideally, you want hundreds or thousands. 3 falls so far below any reasonable threshold that professional statisticians would refuse to analyze it. The error bars on any conclusion would span orders of magnitude. This frustrating reality means that almost every question about interstellar visitor demographics remains unanswered. Are carbon dioxide-rich objects common or rare? Do most interstellar comets show unusual morphology, or is 3I Atlas exceptional? Does the galactic population follow a steep size distribution or a shallow one? We simply don't know, because 3 examples tell us almost nothing. The Vera Rubin Observatory promises to change this situation dramatically. When fully operational, its legacy survey of space and time will scan the entire southern sky every few nights for 10 years. Current projections suggest it might discover dozens or even hundreds of interstellar visitors annually. Within 5 years, we could have statistical samples large enough to actually answer population questions meaningfully. Until then, 3I Atlas exists in a strange limbo. It might be typical, exceptional, or anything in between. The preliminary mass estimates could represent a genuine discovery about interstellar object populations, or a measurement artifact that will be revised downward as more data accumulates. The unusual chemistry might be common among interstellar travelers, or unique to this specific visitor. The interstellar medium should be filled with debris. Stars have been forming, evolving, and ejecting material for billions of years. Theoretical models attempt to predict what this accumulated population looks like, and those predictions don't align well with finding 3I Atlas so early in our survey efforts. Population synthesis models work by combining several ingredients. Start with galactic star formation rates over cosmic history. Add planetary system formation models that predict how much debris gets created. Include ejection mechanisms with their size-dependent efficiencies. Factor in destruction rates during interstellar transit. The output tells you how many objects of various sizes should be wandering through local space at any given moment. Most frameworks predict steep size distributions. For every 5-kilometer object, like 3I Atlas, there should be hundreds or thousands of 1-kilometer objects, and millions of 100-meter specimens. The exact ratios depend on assumptions about ejection physics and survival rates, but the basic pattern remains consistent across different models. Small objects should vastly outnumber large ones. This prediction makes intuitive sense. Planetary systems contain far more small bodies than large ones. Our asteroid belt follows this pattern, the Kuiper belt follows it, and observations of debris disks around other stars suggest the same scaling applies universally. When these systems eject material into interstellar space, they should export the same size distribution they contain. The local interstellar medium, meaning space within a few hundred light-years of our Sun, should contain billions of objects larger than 100 meters based on these models. Most remain invisible unless they pass close enough to develop detectable activity or reflect sufficient sunlight. But encounter rates with our solar system should favor smaller objects simply because they're more numerous. Current estimates suggest one interstellar visitor larger than 100 meters should pass through the inner solar system every year or two. smaller objects come through more frequently, larger ones less often. A 5-kilometer monster, like 3I Atlas, if the mass estimates hold, should be exceptionally rare. We might expect one every decade or century, depending on the specific model. Yet here we are, 3 confirmed interstellar objects, and the latest is potentially the most massive by far. Either we've been extraordinarily unlucky, witnessing a rare event during our first systematic surveys, or the theoretical models need revision. Several possibilities could reconcile theory with observation. Perhaps ejection mechanisms operate differently than models assume, preferentially launching larger objects more efficiently than expected. Maybe survival rates during interstellar transit favor massive bodies more strongly than calculations suggest. Possibly, detection biases are more severe than we recognize, causing us to systematically miss smaller visitors. Another option is that stellar environments vary more than models account for. Dense stellar clusters might produce different size distributions than isolated star formation regions. Binary star systems might eject different debris populations than single stars. Metal-rich systems could behave differently than metal-poor ones. Current models often assume average conditions rather than capturing this diversity. The reservoir problem cuts to fundamental questions about how matter moves through the galaxy. Every star that forms creates a planetary system, or at least a debris disk. Gravitational interactions inevitably eject some fraction of that material. Over billions of years and hundreds of billions of stars, the accumulated debris should fill interstellar space with travelers. Understanding this reservoir matters beyond satisfying curiosity about 3I Atlas. The composition and size distribution of interstellar objects encode information about planetary system formation throughout galactic history. Different formation environments produce different debris signatures. By studying what arrives at our solar system, we learn about conditions in stellar nurseries across space and time. The most conservative scientific position treats 3I Atlas as an unusual but ultimately natural object. This framework acknowledges the anomalies while maintaining that comet physics we don't fully understand can explain everything without invoking exotic scenarios. Start with the morphology. The persistent sunward glow and unusual tail structure look strange, but anti-tails have appeared in solar system comets for decades without revolutionizing our understanding. Forward, scattering by dust grains with specific size distributions and compositions can create brightness enhancements that appear to point toward the sun. The effect requires particular combinations of grain properties and viewing geometry, but nothing that violates known physics. The dust-to-gas ratio offers another natural explanation. If 3I Atlas produces more dust relative to gas than typical comets, or if its dust grains have different compositions affecting how they scatter light, the visible morphology could differ from expectations without requiring anything fundamentally new. Different ice compositions sublimate at different rates, entraining dust in different patterns. The carbon dioxide-rich chemistry fits naturally within this framework. Formation in the frigid outer regions of a distant planetary system, beyond where carbon dioxide freezes solid, explains the unusual volatile ratios without invoking anything exotic. Solar system comets show a range of compositions depending on where they formed. 3I Atlas simply represents the extreme cold end of that spectrum, born in conditions we don't often sample locally. The nickel emissions without iron present a chemistry puzzle, but several natural mechanisms could produce this pattern. Photostimulated desorption might release nickel-bearing compounds, preferentially if they're more susceptible to ultraviolet breakdown than iron-bearing materials. Thermal decomposition of organic metallic complexes could selectively liberate nickel at the temperatures 3I Atlas experienced. Laboratory studies of sublimation chemistry under comet-like conditions might reveal pathways we haven't considered yet. Even the mass acceleration disconnect might have natural resolution. The calculations depend on assumed outflow rates and gas velocities derived from models. If those models don't perfectly capture what's happening, perhaps because of unusual surface properties or exotic ice physics, the inferred mass could be overestimated. Maybe the gas escapes less efficiently than assumed, or momentum transfer works differently for carbon dioxide-dominated activity. Measurement uncertainties also matter. The acceleration upper limit, while impressively small, still has error bars. The spectroscopic estimates of gas production have uncertainties. Each parameter in the mass calculation chain carries some imprecision, and those uncertainties compound. The 33 billion ton figure represents a lower limit based on assumptions that individually seem reasonable, but collectively might not capture the full complexity. This conservative approach emphasizes that unusual doesn't automatically mean unprecedented. Comets are complex objects with intricate physics governing sublimation, dust dynamics, and momentum transfer. Our understanding comes primarily from solar system specimens, which might not represent the full diversity of behavior possible across different formation environments. The natural anomaly framework serves important scientific functions. It prevents premature conclusions based on incomplete data. It reminds researchers that conventional physics often explains apparently mysterious phenomena once better measurements arrive. It maintains healthy skepticism toward extraordinary claims while the evidence remains preliminary. History supports this caution. Many astronomical anomalies that initially seemed to challenge fundamental physics eventually received mundane explanations as observations improved and models became more sophisticated. The scientific process self-corrects through exactly this kind of rigorous evaluation. The planet seeding hypothesis represents one of the most intriguing theoretical frameworks for understanding massive interstellar visitors like 3I Atlas. The concept, advanced by researcher Suzanne Faulkner, suggests that captured interstellar objects could bypass traditional planet formation bottlenecks and jumpstart giant planet growth. Traditional planet formation faces a significant timing problem. Giant planets must grow to substantial sizes before their parent protoplanetary disks dissipate through photoevaporation and stellar accretion. This process typically occurs within 5 to 10 million years of stellar birth, creating tight constraints on how quickly planetary cores can accumulate enough mass to trigger runaway gas collection. Core accretion models struggle with what astronomers call the meter-size barrier. Growing planet embryos feel significant drag from disk gas, causing orbital decay that prevents growth to planet-size scales before they spiral into their parent stars. Small debris gets pulled inward faster than it can accumulate into larger gravitationally bound objects. Interstellar object capture offers an elegant solution. If young stellar systems can gravitationally snare pre-existing kilometer-scale objects from passing debris, these ready-made seeds bypass the slow growth phase entirely. The captured objects already possess sufficient mass to resist aerodynamic drag while providing gravitational scaffolding for rapid planet assembly. Conference presentations at the 2025 European Planetary Science Congress provided updated simulations supporting this scenario. New modelling indicates that massive stars capture interstellar objects more efficiently than lower mass stellar systems. More massive stars create deeper gravitational potential wells that increase capture cross-sections for passing objects. Additionally, massive stars often form in dense clusters, where encounter rates with interstellar debris remain high during critical early disk phases. The chemistry connection adds plausibility to seeding scenarios involving 3I Atlas. JWST detected carbon dioxide-rich outgassing with abundance ratios suggesting formation far beyond the carbon dioxide snowline, where temperatures remain below -125 degrees Celsius. Such frigid formation conditions would be typical for objects originating in stellar system peripheries. A captured interstellar visitor carrying foreign volatile compositions could introduce chemical diversity into its new host disk. Different stellar systems likely produce debris with different ice compositions and element abundances, so capture processes would mix material from multiple stellar environments across the galaxy. Population statistics become crucial for evaluating hypothesis viability. If Vera Rubin Observatory discovers numerous interstellar visitors over the next decade, capture rates in young stellar systems become statistically plausible. If 3I Atlas proves exceptionally rare, seeding scenarios lose credibility due to insufficient raw material availability. The process becomes most efficient during the first few million years, when stellar systems retain circumstellar disks massive enough to support rapid accretion onto captured seeds. Capture efficiency depends on relative velocity between interstellar visitors and target systems, disk mass and structure, and presence of binary companions or cluster environments modifying gravitational dynamics. The technological interpretation of 3I Atlas emerges from a convergence of unusual characteristics that, when viewed collectively, challenge conventional explanations. Harvard astronomer Avi Loeb has been among the most prominent advocates for taking this possibility seriously, though his actual statements prove more nuanced than headlines often suggest. Loeb typically frames artificial origins as hypotheses requiring further investigation, rather than established conclusions. His approach involves calculating probabilities for various natural scenarios and comparing them with alternative explanations when conventional physics appears insufficient. This represents legitimate scientific methodology, generating testable hypotheses rather than making definitive claims. The ecliptic alignment provides a foundation for these arguments. 3I Atlas approaches with an orbital inclination of just 4.1 degrees relative to the planetary plane. This configuration occurs randomly in only about one case out of 500 for objects arriving from arbitrary interstellar directions. While not impossible, such precise alignment raises eyebrows among researchers tracking visitor statistics. The mass to acceleration disconnect adds weight to technological speculation. If 3I Atlas truly weighs tens of billions of tons with minimal non-gravitational acceleration, despite active outgassing, conventional comet physics struggles to accommodate such behavior. Proponents suggest that controlled propulsion could explain the disconnect between visible activity and missing orbital perturbations. The perihelion timing creates another talking point. The object reaches closest approach to the Sun on the far side from Earth's perspective, creating months of observational blackout due to solar glare. Some coverage describes this as intentional evasion, though others correctly explain it as straightforward orbital mechanics. The trajectory follows physics, not navigation decisions. Multiple papers outline technically challenging but potentially feasible mission concepts for redirecting NASA's Juno spacecraft toward a close encounter with 3I Atlas during its March 2026 passage near Jupiter. These proposals demonstrate genuine scientific ambition to obtain close-up data rather than relying solely on remote observations. The fuel requirements push engineering limits, but the calculations show it's not impossible. Congressional interest reached official levels when representatives sent a letter to NASA urging detailed study of repurposing Juno for interstellar object investigation. This political attention underscores extraordinary public fascination and reflects growing recognition that such opportunities may not arise again for decades. Testable predictions distinguish scientific speculation from unfounded conjecture. If 3I Atlas were indeed artificial, it might exhibit sudden trajectory changes beyond what outgassing predicts. After perihelion passage, such deviations would appear as unexplained accelerations in continued monitoring. Alternative signatures might include non-thermal emission patterns, coherent radio transmissions, or polarization characteristics inconsistent with natural dust. The burden of proof discussion becomes crucial. Extraordinary claims require extraordinary evidence. Absence of ion emissions or anomalously small accelerations might seem suggestive, but they don't constitute positive evidence for artificial propulsion. Current observations, while unusual, fall short of definitive proof necessary to invoke technological explanations. NASA and the European Space Agency maintain positions of treating 3I Atlas as natural unless compelling data suggests otherwise. This institutional stance represents standard scientific conservatism, a methodological approach that assumes conventional explanations until observations definitively rule them out. The space agencies continue monitoring the object with available assets while avoiding premature conclusions about its nature or origins. This cautious approach serves multiple purposes. It prevents resources from being diverted based on speculation rather than evidence. It maintains public confidence in scientific rigor. It avoids the embarrassment of official endorsement for ideas that might not withstand scrutiny. Both organizations released statements acknowledging the unusual characteristics observed in 3I Atlas, while emphasizing that current data remains consistent with natural comet behavior, albeit at the extreme end of what we've observed previously. The statements carefully avoid dismissing alternative hypotheses, while making clear that extraordinary claims require extraordinary evidence. NASA's official position emphasizes that the perihelion passage behind the Sun results from orbital mechanics, not deliberate concealment. The agency's geometric analysis explains that 3I Atlas follows a hyperbolic trajectory determined by its initial velocity vector and solar gravitational physics. The timing that places closest solar approach on the far side relative to Earth represents mathematical coincidence, not conscious navigation. This explanation matters because media coverage sometimes frames the perihelion timing as suspicious, as if the object were intentionally avoiding observation. NASA's clarification serves an educational function, helping the public understand that orbital paths follow deterministic physics rather than decision-making processes. The European Space Agency takes similar positions regarding observations from Mars orbiting spacecraft, while acknowledging the scientific value of any data collected during the October 2025 Mars encounter. ESA statements emphasize that participation depends on technical feasibility and resource constraints, rather than assumptions about the object's nature. Both agencies face challenging communication tasks. They must balance legitimate scientific excitement about an unusual discovery with appropriate caution about preliminary findings. They need to keep options open for potential spacecraft missions, while avoiding commitment to expensive endeavors based on incomplete data. They must engage public interest without fueling unfounded speculation. The institutional conservatism extends to mission planning decisions. While researchers have outlined concepts for redirecting Juno toward 3I Atlas, NASA has not committed to such plans. The agency continues evaluating technical feasibility, scientific merit, and opportunity costs. Redirecting Juno would end its primary Jupiter science mission, trading guaranteed returns against uncertain gains from interstellar visitor investigation. This deliberative approach frustrates some researchers who view 3I Atlas as a once-in-a-generation opportunity requiring bold action. But institutional caution serves important functions in managing public resources and maintaining scientific credibility. Premature commitments based on preliminary data can backfire if subsequent observations reveal the situation differs from initial impressions. The media ecosystem surrounding 3I Atlas reveals how scientific uncertainty transforms into public narrative through successive layers of interpretation. Initial research papers presenting preliminary findings evolve through press releases, news articles, social media posts, and commentary until original caveats sometimes disappear entirely. The process begins with researchers publishing preprints or conference presentations. These early-stage communications serve legitimate scientific functions, enabling rapid information sharing before formal peer review. The 3I Atlas mass estimates circulated through preprint servers before full publication, allowing the community to evaluate methods and assumptions while observations continued. Press offices at universities and research institutions then translate technical findings into accessible language for journalists. This translation step involves judgment calls about which details to emphasize and how to frame uncertainties. A careful press release might describe mass estimates as preliminary lower limits requiring further confirmation. A less careful one might present the numbers more definitively. Journalists working under deadline pressures condense press releases into news articles. Each condensation step risks losing nuance. Phrases like preliminary lower limit might become estimated mass in headlines. Unusual, but potentially natural, might transform into mysteriously anomalous. The caveats shrink while the extraordinary aspects grow more prominent. Social media amplification creates feedback loops where initial coverage generates commentary that references itself. A speculative blog post citing a news article summarizing a press release about preliminary research can gain viral traction, getting shared thousands of times. Successive retellings strip away remaining caveats, transforming possibilities into apparent certainties. The 3I Atlas coverage demonstrates this progression clearly. Initial papers carefully presented mass calculations as model-dependent lower limits. Early news coverage mostly preserved these caveats. But as the story spread through social media and secondary outlets, some versions began presenting the 33 billion ton figure as established fact rather than preliminary estimate. The technological interpretation followed similar amplification paths. Avi Loeb's actual statements, which typically frame artificial origins as hypotheses requiring investigation, sometimes got reported as claims that 3I Atlas is probably artificial. The distance between presenting an idea for consideration and asserting it as likely truth can disappear through repeated retelling. Second-tier websites and social media accounts amplified narratives about nickel emissions supposedly indicating manufactured materials. The VLT team presented their spectroscopic results as interesting natural chemistry, but some coverage jumped to implications of artificial composition. The gap between unusual chemistry and technological origin is vast, but successive retellings sometimes bridged it without justification. Educational opportunities emerge from examining this amplification process. 3I Atlas provides real-time examples of how scientific information evolves through communication channels with different standards and incentives. Understanding these dynamics helps people evaluate claims more critically. Quality science journalism distinguishes between what researchers actually say and how statements get interpreted by others. Careful reporting includes appropriate caveats about preliminary findings, acknowledges competing explanations, and provides context about typical scientific methodology for evaluating extraordinary claims. The cosmic choreography, bringing 3I Atlas within 30 million kilometers of Mars on October 3rd, 2025, creates an unprecedented opportunity for multi-vantage point observations of an interstellar visitor. This encounter distance of roughly 0.2 astronomical units places the object well within operational range of Mars-orbiting spacecraft. European Space Agency missions currently operating around Mars include Mars Express, launched in 2003 and still functioning after more than 2 decades, and the Trace Gas Orbiter, which arrived in 2016. Both spacecraft carry imaging systems and scientific instruments that could potentially observe 3I Atlas during its passage, though operational constraints and power limitations require careful mission planning. NASA's MAVEN orbiter, studying Martian atmospheric escape since 2014, represents another potential observer. While primarily designed for atmospheric research rather than deep space observations, MAVEN's instruments might contribute if mission managers can accommodate pointing requirements and data priorities. The Mars Reconnaissance Orbiter faces significant challenges observing 3I Atlas due to enormous distance. Even at closest approach, the object remains tens of millions of kilometers away, far beyond optimal resolution capabilities designed for surface features. Nevertheless, any Mars-based observations would provide valuable constraints on brightness profiles and phase angle effects unavailable from Earth-based telescopes. The different viewing geometry offers perspectives on dust scattering and gas distribution that might appear quite different when observed from Mars versus Earth positions. Independent brightness measurements from Mars orbital perspective would complement Earth observations and potentially resolve discrepancies in activity assessments. Coordination between Mars assets and ground telescopes requires precise timing. Light travel time between Earth and Mars, approximately 16 minutes during encounter, complicates real-time coordination, but allows planned observation sequences designed to maximize scientific return. The geometric advantage becomes apparent when considering Earth's perspective during the same period. From our planet, 3I Atlas appears increasingly close to the Sun in the sky as it approaches perihelion, creating challenging conditions due to solar glare. Mars orbiters face no atmospheric limitations and observe from different geometry. Safety considerations remain minimal given encounter distances. 30 million kilometers represents roughly 75 times the Earth-Moon distance. Close by astronomical standards, but presenting zero collision risk to Mars spacecraft. The Mars Encounter observations represent preview of future multi-asset coordination for studying transient phenomena throughout the solar system. The data collected during Mars Encounter, combined with continuous Earth monitoring, will provide unprecedented temporal and geometric coverage of an interstellar object's evolution as it responds to changing solar heating while approaching perihelion. The gravitational dance, bringing 3I Atlas within 53.6 million kilometers of Jupiter on March 16th, 2026, represents perhaps the most scientifically valuable observation opportunity in the object's entire passage through our solar system. At 0.358 astronomical units from the gas giant, this encounter distance places the interstellar visitor within potential range of NASA's Juno spacecraft, currently conducting extended mission operations in Jovian orbit. Multiple research papers have outlined ambitious mission concepts for redirecting Juno toward an intercept trajectory with 3I Atlas using gravitational assist maneuvers and the spacecraft's remaining fuel reserves. These proposals, developed by teams including Loeb, Hibbard, and other researchers, represent technically challenging but potentially feasible engineering solutions for achieving humanity's first close encounter with an interstellar visitor. The orbital mechanics would require what aerospace engineers call an Oberth effect maneuver, using Jupiter's gravitational field to amplify the effectiveness of Juno's propulsive burns. By firing the spacecraft's engines at closest approach to Jupiter, where orbital velocities reach maximum, each unit of propellant provides maximum momentum change for trajectory modification. Congressional interest reached official levels when representatives sent a letter to NASA urging detailed study of repurposing Juno for interstellar object investigation. This political attention underscores extraordinary public fascination and reflects growing recognition that such opportunities may not arise again for decades or longer. The scientific payoff from successful in situ sampling would dwarf anything achievable through remote observations alone. Juno's instruments could potentially analyze dust composition directly, measure grain size distributions, determine isotopic ratios, and characterize properties that remain impossible using ground-based telescopes or even space observatories operating from Earth vicinity. Direct sampling would provide definitive tests of chemical anomalies inferred from spectroscopic observations. The nickel without iron puzzle, the carbon dioxide-rich ice composition, and other unusual characteristics could be verified or refuted through direct contact with the object's atmosphere and debris trail. The fuel limitations present the primary technical constraint on mission feasibility. Juno was not designed for major trajectory changes and carries limited propellant reserves for station keeping around Jupiter. Reaching 3I Atlas would require expenditure of essentially all remaining fuel, ending any possibility of returning to Jupiter science operations. Engineering assessments must evaluate whether Juno's propulsion system can deliver sufficient velocity change to achieve intercept trajectories within available fuel margins. The calculations involve complex orbital mechanics accounting for Jupiter's gravitational field, the spacecraft's current trajectory, and the predicted path of 3I Atlas through the outer solar system. The observation geometry during Jupiter encounter offers advantages compared with other windows. The outer solar system location provides excellent viewing conditions free from solar interference, though enormous distance from Earth complicates real-time communication and reduces apparent brightness for ground telescopes. Mission timeline constraints add urgency to decision-making. Spacecraft trajectory modifications require months of planning and implementation. If NASA decides to attempt Juno redirection, approval and execution must begin well before actual encounter to allow sufficient time for orbital adjustments. The decision facing NASA represents one of the most challenging trade-offs in recent space mission history. On one side sits guaranteed scientific return from continuing Juno's primary Jupiter mission, studying gravitational fields, magnetic environments, and atmospheric dynamics with unprecedented detail. On the other side lies uncertain but potentially transformative gains from humanity's first close encounter with an interstellar visitor. The fuel constraint dominates all technical considerations. Juno carries limited propellant reserves designed for station keeping and orbital adjustments around Jupiter, not major trajectory changes. Reaching 3I Atlas would consume essentially every drop of remaining fuel. The spacecraft could never return to Jupiter science operations. This becomes a one-way trip, trading years of potential Jupiter observations for a single fleeting encounter with the interstellar object. Engineering teams must evaluate whether the propulsion system can physically deliver sufficient velocity change within available margins. The Oberth effect maneuver helps by amplifying thrust effectiveness at closest Jupiter approach, but the delta V requirements remain substantial. Preliminary calculations suggest feasibility exists, but with little margin for error or course corrections. The scientific merit calculation proves equally complex. Jupiter mission objectives focus on understanding giant planet formation and evolution through detailed mapping. These investigations produce steady, predictable returns, advancing planetary science. The interstellar visitor opportunity offers potentially revolutionary discoveries about galactic debris populations and chemistry, but with higher uncertainty about what might actually be learned. Direct sampling could definitively resolve questions about 3I Atlas's composition, mass, and nature that remote observations leave ambiguous. Instruments aboard Juno could analyze dust grains, measure isotopic ratios, and characterize properties impossible to determine from Earth. This data might answer fundamental questions about interstellar object populations, or reveal the preliminary mass estimates were artifacts of incomplete modeling. Alternatively, the encounter might yield disappointing results if 3I Atlas proves less unusual than initial observations suggested. The object could turn out to be a fairly typical comet with unusual but explainable characteristics. In that scenario, NASA would have sacrificed years of Jupiter science for limited gain. The opportunity cost extends beyond Juno's primary mission. Resources spent planning and executing the redirection, including personnel time and communication infrastructure, cannot be used for other projects. The decision sets precedent for how space agencies respond to future interstellar visitors, potentially affecting resource allocation for decades. Public and political pressure adds complexity. Congressional interest signals that some stakeholders view the opportunity as worth pursuing regardless of technical challenges. But institutional responsibility demands that NASA make decisions based on scientific merit and technical feasibility rather than enthusiasm alone. The timeline creates urgency. Decisions made in coming months determine whether redirection remains feasible. Delay past certain thresholds closes the window permanently, as geometric constraints make intercept trajectories impossible regardless of available fuel. Whatever NASA decides will be scrutinized for years. Choose to redirect Juno, and the Jupiter science community loses planned observations. Choose to continue primary mission, and critics will argue a once-in-a-generation opportunity was squandered. There are no perfect answers, only difficult trade-offs between competing legitimate priorities. The cosmic geometry of 3I Atlas's orbit creates a months-long observational blackout precisely when astronomers want to watch most closely. The object reaches perihelion, its closest approach to the Sun, on the far side of our star from Earth's perspective. This timing results purely from orbital mechanics, not deliberate concealment, but it frustrates observation plans nonetheless. As 3I Atlas approaches the Sun through late September and October 2025, it draws increasingly close to our star's position in Earth's sky. Solar glare overwhelms the faint light reflected from the comet, making ground-based observations progressively more difficult. By the time perihelion arrives, the object sits behind the Sun from our viewpoint, completely invisible to Earth-based telescopes. This blackout period extends for weeks as the interstellar visitor swings around the Sun and begins its outbound journey. Only gradually does it emerge from behind solar glare into observable sky positions again. The most dynamically active phase, when solar heating peaks and sublimation reaches maximum intensity, occurs precisely when direct Earth observation becomes impossible. The perihelion distance brings 3I Atlas to within the orbit of Venus, exposing it to intense solar radiation. Surface temperatures spike, driving sublimation rates to their highest levels. Chemical reactions that remain dormant at greater distances suddenly activate. The object's appearance and activity patterns should change dramatically during this phase, yet Earth-based astronomers cannot watch it happen in real time. Parker Solar Probe offers a unique exception to this observational drought. The spacecraft, designed to study the Sun's corona from extremely close range, orbits within the inner solar system, where its whisper camera can potentially observe 3I Atlas from solar perspectives unavailable to Earth. During late September through early November 2025, Parker Solar Probe occupies positions where the interstellar visitor remains visible despite Earth's blackout. These space-based observations could reveal activity patterns or morphological changes invisible from the terrestrial viewpoints. The different viewing geometry might resolve questions about the unusual sunward glow and evolving tail structure. Dust scattering properties that create ambiguous signatures from one angle might appear clearer from another. The observational gap creates scientific frustration, but also demonstrates limits of current infrastructure. A single Earth-based civilization cannot maintain continuous coverage of objects that pass behind the Sun. Future missions to solar orbit positions, different from Earth's, could eliminate these blind spots, but no such assets currently exist with capabilities for observing distant comets. The perihelion blackout forces astronomers to rely on before and after comparisons, rather than continuous monitoring. Pre-perihelion observations through September establish baseline activity levels and morphology. Post-perihelion observations, beginning in late November or December, will reveal how the close solar passage changed the object. But the transition itself remains largely hidden from view. The next 18 months represent the most data-rich observation window ever available for an interstellar visitor. From discovery in July 2025 through final observations as the object departs the inner solar system in late 2026, multiple space-based and ground-based facilities will track 3I Atlas through its complete passage around the Sun. This extended campaign provides unprecedented temporal coverage of how an interstellar object responds to varying solar heating. As 3I Atlas approached through summer and fall 2025, observations documented steadily increasing activity. Water ice sublimation activated around 3 astronomical units from the Sun. Carbon dioxide became prominent much earlier. Each volatile species began releasing gas at characteristic distances corresponding to different temperature thresholds. The morphological evolution captured by Hubble, Gemini, and other facilities shows real-time changes as different surface regions warm and cool. Early images revealed predominantly the unusual sunward glow. Later observations developed more traditional tail structures. This evolution provides crucial tests of dust dynamics, models attempting to explain the object's appearance. JWST spectroscopy on August 6th established chemical baselines showing carbon dioxide-rich composition. Follow-up observations as the object continues. Its journey will reveal whether volatile ratios change as different ice layers become exposed. The chemistry might evolve if the nucleus has layered structure with varying compositions at different depths. The VLT nickel emission detections provided snapshots at specific distances. Continued spectroscopic monitoring will show whether metal release mechanisms change with temperature or remain constant. If photostimulated desorption drives the process, emission rates should correlate with solar ultraviolet flux intensity. Ground-based astrometry continues accumulating position measurements throughout the campaign. The 4,000+ measurements through September represent just the beginning. Extending observations through 2026 will either confirm the anomalously small acceleration or reveal deviations that emerge only after perihelion passage, when activity patterns change. The Mars encounter in October 2025 adds multi-vantage point perspective. Any observations from Mars orbiters complement Earth-based data by providing different viewing geometry and simultaneous coverage during periods when terrestrial telescopes face challenging solar angles. The potential Jupiter encounter in March 2026, whether through Juno redirection or remote observations, represents the campaign's climax. At that distance, 3I Atlas will have passed perihelion and begun cooling. Comparing pre- and post-perihelion characteristics reveals how close solar passage affected the object's properties and behavior. The perihelion blackout creates a gap in coverage, but Parker Solar Probe's WHISPER camera potentially fills part of this window with observations from unique solar perspectives. Before and after comparisons bracket the most active phase, even if continuous monitoring proves impossible. The theoretical implications of 3I Atlas extend far beyond single object characterization into fundamental questions about interstellar debris populations, planetary system formation mechanisms, and chemical evolution of matter throughout galactic history. Whether preliminary mass estimates prove accurate or require significant revision, the object has already forced astronomers to confront gaps in understanding that will drive research directions for years to come. If subsequent analysis confirms the 5-kilometer nucleus diameter and 33 billion ton mass estimates, interstellar object population models face serious challenges explaining how such massive debris gets ejected from planetary systems and survives transport through interstellar space. Current ejection mechanisms struggle to launch objects this large efficiently, suggesting either theoretical frameworks need updating, or 3I Atlas represents an extreme statistical outlier that happened during humanity's first serious surveys. The population statistics problem would demand new theoretical work on ejection processes, particularly mechanisms capable of launching massive objects without destroying them through tidal forces or collision cascades. Stellar flyby scenarios might need re-evaluation, while planet-to-planet scattering models would require examination of rare geometric configurations that could eject kilometer-scale objects without fragmentation. Alternatively, if future observations reduce mass estimates to more conventional values, the lesson becomes one about how atmosphere physics and outgassing dynamics can mislead observers into inferring incorrect physical properties. Such an outcome would represent a significant advance in understanding non-gravitational forces and their relationship to observable comet characteristics. Chemistry pathways for explaining the nickel without iron emission pattern will likely generate extensive theoretical investigation, regardless of ultimate mass determination. The selective appearance of nickel lines, without corresponding iron features, challenges standard models of metal release, mechanisms in cometary atmospheres, suggesting either exotic chemical compounds or unusual physical processes operate differently than in typical comets. Photodesorption models, thermolysis scenarios involving organic metallic complexes, and differential sublimation of metal-bearing phases all represent theoretical frameworks that could potentially explain observed emission patterns. Testing these alternatives requires detailed laboratory experiments and sophisticated chemical modeling of low-temperature, low-pressure environments, characteristic of comet atmospheres. The carbon dioxide-rich chemistry detected by JWST adds another theoretical challenge by indicating formation conditions quite different from typical solar system comet birth environments. Understanding how objects form with such unusual volatile compositions requires models of chemical evolution in outer regions of stellar systems, where temperatures remain below -125 degrees Celsius. Morphological modeling efforts will focus on explaining the persistent sunward glow and evolving anti-tail structure through dust dynamics and viewing geometry effects. These theoretical investigations could advance general understanding of how dust grains behave in comet atmospheres, with applications extending beyond interstellar visitors to solar system comets exhibiting similar phenomena. Population consequences of 3I Atlas observations will drive theoretical work on interstellar object demographics and implications for planetary system formation throughout the galaxy. If massive visitors prove common, theoretical frameworks for understanding debris ejection and transport between stellar systems will require fundamental revision. The Vera-Rubin Observatory's impending flood of interstellar object discoveries will provide statistical constraints on population models within the next few years. Theoretical predictions about size distributions, chemical compositions, and orbital characteristics can be tested against large samples rather than speculative extrapolation from individual examples. The Vera-Rubin Observatory represents astronomy's next revolution in transient discovery. When the legacy survey of space and time begins full operations, it will scan the entire southern sky every few nights for 10 years. This systematic approach will transform interstellar object astronomy from opportunistic discovery into statistical science, with sample sizes large enough to answer questions that currently remain pure speculation. Current projections suggest Rubin might discover dozens or even hundreds of interstellar visitors annually. Within 5 years, astronomers could accumulate statistical samples orders of magnitude larger than the 3 examples we have today. The transition from anecdotes to population studies will finally become possible. If 3I Atlas truly represents typical visitor mass rather than an extreme outlier, Rubin should detect similar giants regularly. The survey's sensitivity and cadence are optimized for catching fast-moving transients, making it ideal for spotting interstellar objects as they pass through the inner solar system. Multiple detections of massive visitors would force revision of ejection mechanism models and population predictions. Alternatively, if Rubin floods discovery lists with smaller, more typical specimens, while massive objects like 3I Atlas remain rare, that would confirm the population paradox as real. We would know definitively that finding the elephant before the mice represented genuine statistical anomaly rather than observational bias. The size distribution revealed by Rubin observations will constrain theoretical models of ejection physics and interstellar survival rates. If the distribution follows steep power laws with small objects vastly outnumbering large ones, current models work reasonably well. If the distribution proves flatter with more large objects than expected, something about ejection mechanisms or destruction rates needs fundamental rethinking. Chemical diversity within the interstellar visitor population will become mappable once sample sizes grow. Is carbon dioxide rich composition, like 3I Atlas, common or exceptional? Do most interstellar comets show unusual metal emissions, or does that represent special case chemistry? Only large samples can answer these questions definitively. Orbital characteristics across many visitors will reveal whether the 4.1 degree ecliptic alignment of 3I Atlas was coincidence, or indicate something about how detection biases shape observed populations. If most discoveries show similar alignments, we know surveys favor ecliptic plane objects. If inclinations distribute randomly, the alignment was just luck. The morphological diversity will emerge from systematic observations. Does the unusual sunward glow and anti-tail structure appear commonly or rarely? Understanding whether 3I Atlas represents typical morphology versus exotic appearance requires comparison with many other visitors under similar observing conditions. Rubin's rapid cadence enables tracking of how activity evolves as objects warm approaching the sun. Rather than snapshots at discrete times, astronomers will capture continuous evolution, documenting when different volatile species activate and how dust production responds to changing temperatures. The observatory will also catch visitors at greater distances, where they're fainter and less active. Current surveys tend to find interstellar objects only after they've approached close enough to develop visible atmospheres. Rubin's sensitivity might detect them farther out, revealing whether distant activity differs from what we observe closer to the Sun. Within a decade, the field will transition from studying individual unusual objects to analyzing population statistics with robust sample sizes. Questions about ejection mechanisms, survival rates, chemical diversity, and size distributions will shift from theoretical speculation to empirical measurement. 3I Atlas will be remembered as the object that raised these questions, but Rubin will provide the answers. As 3I Atlas continues its journey back toward interstellar space, carrying with it more questions than answers, we find ourselves confronting a fundamental shift in how we understand our place in the cosmic order. This silent giant from between the stars has forced us to acknowledge that the universe operates on scales and through processes that still challenge our most sophisticated theoretical frameworks. Whether the preliminary mass estimates prove accurate or require revision, whether the chemical anomalies receive conventional explanations or reveal genuinely new physics, 3I Atlas has already accomplished something remarkable. It transformed interstellar object astronomy from curiosity-driven investigation into systematic scientific inquiry. The techniques developed to study this enigmatic visitor will serve astronomy for generations. Precision astrometry campaigns involving hundreds of observatories, rapid response protocols, connecting space and ground-based assets, sophisticated chemical modeling of exotic volatile compositions. These tools will benefit every future interstellar traveler we encounter. Perhaps more importantly, this object demonstrated that the space between stars is not empty wasteland, but rather a dynamic reservoir of material carrying information about planetary formation processes operating throughout galactic history. Each interstellar visitor represents a messenger from stellar environments we can never visit directly, bearing chemical and physical signatures of conditions in alien solar systems billions of years ago. The planet seeding hypothesis, technological speculation, population statistics puzzles, and chemical mysteries surrounding 3I Atlas will continue driving scientific investigation long after the object itself fades from telescopic view. The questions it raised about ejection mechanisms, survival processes, and detection biases touch fundamental aspects of how matter moves through the galaxy. In a broader sense, 3I Atlas embodies the essential uncertainty that makes science compelling. We live in an era where astronomical observations can surprise us, where preliminary data can challenge established frameworks, and where the next discovery might revolutionize our understanding of how the universe works. That capacity for surprise, for genuine discovery, represents one of humanity's most precious intellectual assets. As we prepare for the flood of discoveries that next generation surveys will provide, 3I Atlas stands as a reminder that individual objects can still capture imaginations and drive scientific progress in unexpected directions. The transition to statistical analysis of large populations should not diminish appreciation for the unique characteristics that make certain visitors special. The legacy extends beyond astronomy into how we think about evidence evaluation, hypothesis testing, and the gradual accumulation of knowledge that drives scientific progress. 3I Atlas provides a case study in how communities respond to genuinely anomalous observations with excitement tempered by appropriate skepticism, speculation balanced by rigorous methodology. In the end, whether 3I Atlas proves to be a massive natural comet carrying exotic chemistry from alien stellar environments, a statistical outlier that appeared during humanity's first systematic interstellar surveys, or something even more extraordinary. It has already earned its place in astronomical history. It forced us to look more carefully at our assumptions, develop better observational techniques, and think more deeply about processes operating on galactic scales. The silent giant continues its journey back toward interstellar space, but the questions it raised and the techniques developed to study it will shape astronomy for decades to come.